Welcome to the Deep Dive. Today, we're doing exactly that, plunging into some fascinating new research. It really pulls back the curtain on how the latest, most advanced AI models are, well, thinking.
Or perhaps not thinking, especially when things get tricky.
Right, we're talking about these systems that go beyond standard chatbots. What are they called again? LRMs.
That's it. Large reasoning models. They're built with, specific mechanisms designed to mimic step-by-step logic, even maybe some self-correction.
And we're basing this whole discussion on a paper from Apple. The title alone is pretty provocative. The Illusion of Thinking. Understanding the strengths and limitations of reasoning models via the lens of problem complexity.
Yeah, it definitely catches the eye. So our mission today is pretty straightforward. Unpack this paper, pull out the key insights based only on what these researchers found.
We want to show you where these supposed thinking AI models actually perform well, and, maybe more interestingly, where they seem to fail quite surprisingly.
Get ready for some counterintuitive stuff.
Yeah.
The research suggests that as problems get harder, these models can behave in ways you just wouldn't expect.
But hitting a sudden hard wall in their capability. So yeah, let's dig in.
Okay, first things first. Let's set the stage properly. As you said, LRMs are like LLMs, but with extra layers. Things like chain of thought or these self-reflection steps built in.
So we're talking about models like OpenAI's O1 or O3, DeepSeek R1, that sort of thing.
Exactly. And Claude 3.7 Sonnet Thinking, Gemini Thinking 2, they're all designed to actually generate those intermediate reasoning steps to show their work, so to speak.
But the paper argues that testing them on standard stuff, like, say, math problems or coding challenges, isn't always a clean test, right?
Precisely. There's this issue of data contamination. The models might have just seen very similar problems during their training, so are they reasoning or just recalling patterns, memorizing?
And those benchmarks usually just check the final answer anyway, not how the model got there.
Right. You don't really see the thought process. So to get around that, to really test the reasoning itself under controlled conditions, this paper did something clever.
Instead of those benchmarks.
They used puzzle environments, simple rule-based puzzles.
Ah, okay. And the advantage there is?
You can control the complexity very precisely. Just dial it up or down. And crucially, the rules are given right in the prompt, so the model has to try and use algorithmic logic based only on those rules. It can't rely on having seen the specific puzzle solution before.
Makes sense. What kind of puzzles did they use?
4 main types. First, the classic Tower of Hanoi. Moving disks between pegs, bigger ones can't go on smaller ones.
Right, and that gets hard fast.
Exponentially hard. The minimum moves needed is 2 to the power of n, where n is the number of disks. It blows up quickly.
Okay, what else?
Then there was checker jumping, swapping red and blue checkers on a line, with 1 empty space for moves. Its complexity grows quadratically with the number of checkers, n. So n plus 1 squared minus 1 moves. Still gets harder, but not quite as explosively.
Got it.
2 more.
River crossing puzzles. Think missionaries and cannibals type problems. Moving groups across a river in a boat, respecting capacity limits and safety rules.
Like, you can't leave certain groups unsupervised if they outnumber others.
Exactly. Complexity there depends on the number of pairs being moved, and the boat size is also a factor.
And the last one?
Blocks world. Basically, rearranging stacks of blocks according to rules, like only moving the top block, placing it on the table or another block, requires planning.
So these puzzles let them systematically increase the difficulty and actually look inside the model's thinking trace, the steps it generated.
Precisely. They could analyze both the final answer and the intermediate steps.
Okay, so they ran the models through these puzzles. What was the first big takeaway? Finding number 1.
Well, they compared pairs of models like Claude 3.7 Sonnet with thinking versus without, DeepSeek R1 versus its base model using the same amount of compute power. And they found performance falls into 3 pretty distinct regimes based on how complex the puzzle instance was.
3 regimes. Okay, what's the first one? Low complexity.
Yeah. And this was pretty surprising. At low complexity, the standard models, the ones without the explicit thinking steps, were often more accurate.
More accurate.
More efficient. They used fewer tokens.
Hmm.
It seems like for the easy stuff, the extra thinking machinery in the LRMs didn't help. It might have even gotten in the way. Plus, it costs more compute.
Wow. Okay, that's immediately counterintuitive. Making them think more made them worse on simple tasks.
That's what this data suggests, yeah. Now, the second regime. Medium complexity.
Here.
Here is where the LRMs, the thinking models, started to show their value. Their accuracy pulled ahead of the standard models. The performance gap between the thinking and non-thinking versions widened.
Okay, that feels more like what you'd expect. When it gets a bit harder, the structured thinking helps.
Right, but then you hit the third regime, high complexity.
And what happens there? Does the gap widen further?
No, this is the really striking part. Both the standard models and the advanced LRMs just collapsed. Complete performance collapse. Accuracy dropped to near zero.
Wow, both of them. Even the ones designed for reasoning.
Yeah. The thinking models might have delayed that collapse point just a tiny bit compared to the standard ones, but they ultimately hit the same fundamental wall. They couldn't solve the really hard versions of the puzzles.
So for you listening, this first finding is crucial. These advanced thinking models, they aren't universally better. They seem to have a sweet spot at medium difficulty, but there's a clear, hard limit. Beyond that, they just fail.
Absolutely. And this collapse led them to the second key finding, which is maybe even more counterintuitive. They zoomed in on just the LRMs, different ones like O3 mini variants, DeepSeek R1, Claude 3.7 Sonnet Thinking, and looked closely at how they failed as complexity ramped up.
Okay, what did they see in the failure mode?
Well, naturally, accuracy goes down, then drops off sharply to zero beyond a certain point, which varied a bit depending on the specific model. But the weird part was about the effort the models were putting in.
Effort. How do you measure AI effort?
They looked at the number of thinking tokens the model generated, basically. The length of its internal reasoning or chain of thought output.
Okay. And what happened with those tokens?
Initially, as the problems got harder, the number of thinking tokens increased, which makes sense, right? Harder problem, you'd expect it to think more, spend more effort.
Yeah, like me staring at a Sudoku longer if it's a tough one.
Exactly. But then, as the problems got even harder, right around the point where accuracy collapsed to zero, the number of thinking tokens actually started to decrease.
Wait, it decreased. They used less thinking when the problem was hardest.
That's what the data showed. Even though they had plenty of token budget left, they weren't just hitting a hard limit on output length. They seemed to reduce their reasoning effort precisely when the problems became too difficult for them.
That's bizarre. It's like they just get overwhelmed and stop trying as hard.
It certainly seems that way. It suggests the limitation isn't just about compute budget or output length. It might be a more fundamental scaling issue in their ability to apply complex reasoning. They get lost. Or maybe the internal process just breaks down and stops generating useful steps.
So you can't just assume giving them more thinking time or a bigger token limit will solve ever harder problems.
Yeah.
There seems to be a point where the internal capability just can't keep up, regardless of budget.
Precisely. It challenges that simple scaling hypothesis. And because they were using these puzzles, they could dig even deeper. Which brings us to the third key finding, looking inside the thoughts.
You mean analyzing the actual intermediate steps they generated in that thinking trait?
Exactly. The puzzle setup is great for this because each step, each intermediate state the model proposes, can be checked against the puzzle rules. Is this a valid move? Is this a valid board state?
Right. So what did they find when they looked inside? Any patterns?
Oh, yes. And the patterns depended on the complexity regime again. At low complexity, remember where the standard models were often better.
Yeah.
Here, the LRMs often generated a correct solution quite early in their thinking trace. Like, they found the answer quickly, but then they kept going.
Kept going.
Yeah, they'd continue generating more steps after finding a valid solution path, often exploring incorrect moves or states. Like, it looked like, well, overthinking.
So they solved it but didn't realize it and then potentially confused themselves. That sounds really inefficient.
It definitely suggests inefficiencies and maybe limited self-correction or state tracking. They don't seem to reliably know when they're done or when they've gone down a wrong path after finding a right one.
Okay, what about medium complexity, where the LRMs did better overall?
There, the pattern kind of flicked. They tended to explore incorrect paths first, generating wrong moves or invalid states initially. Then later in the thinking process, they'd stumble upon the correct solution path.
So more of a messy search process before finding the right way.
Seems like it. Less efficient than finding it early, but eventually getting there, which explains the better performance compared to standard models in this regime.
And high complexity, where everything collapsed.
In that regime, the thinking traces were basically useless. They contained no correct steps towards the solution. The internal process was just completely off track, generating invalid moves or getting stuck.
Wow. So looking inside really shows that the thinking isn't always a clean, logical progression. It can be surprisingly messy. Finding the answer early and then getting lost or wandering around randomly before finding it, or just Nothing useful at all.
It definitely adds nuance to what we mean by reasoning in these models, which leads nicely into the fourth finding, which highlights some really puzzling limitations about execution and consistency.
Okay, what was so puzzling here?
This one is pretty stark. Remember the Tower of Hanoi puzzle?
Yeah, the disks.
For that puzzle, they didn't just ask the model to solve it. In some experiments, they actually gave the model the explicit step-by-step algorithm for solving Tower of Hanoi, right there in the prompt.
Wait, they gave it the cheat sheet, like literally the instructions. Step 1, move disk X from peg Y to peg Z.
Pretty much, yeah, the formal recursive algorithm. Now, you'd think, okay, following explicit instructions should be way easier than figuring out the strategy yourself, right? Especially for a computer.
Absolutely. Executing a known algorithm feels like it should be trivial compared to inventing one.
You'd think. But the paper found that even when provided with the explicit algorithm, the model's performance on complex Tower of Hanoi instances, high-N, did not significantly improve.
So seriously?
Seriously. And the performance collapse still happened at roughly the same complexity threshold.
That's genuinely baffling. If it can't reliably follow a given recipe for a complex version of the task, what does that say about its ability to, execute logic precisely?
It's a big question mark. It suggests the bottleneck isn't just about finding the strategy, but maybe about the fundamental ability to track state, apply rules consistently, and follow a long sequence of logical steps without error, especially as the state space, all the possible configurations, gets huge.
It's like they can understand the individual steps, maybe, but lose track of the overall process when it gets long or complicated.
That could be one interpretation. It points to potential limitations in reliable symbolic manipulation over extended sequences. And it wasn't just about execution. There was also this weird inconsistency across different puzzles.
Oh, sorry.
They looked at how many correct moves a model typically made before making its first mistake. And it varied wildly depending on the puzzle type.
Give me an example.
Okay, so Claude 3.7 Sonnet Thinking, on a complex Tower of Hanoi, like N10, which needs over 1,000 moves ideally, could sometimes make over 100 correct moves in a row before messing up. Pretty good, right?
Yeah, that sounds quite capable.
But then, on a river crossing puzzle with N3, which has an optimal solution of only 11 moves, much, much shorter, the same model often failed after just 4 correct moves.
Wow, so it can handle over 100 steps correctly in one context, but trips up after only 4 steps in another, much simpler context. That doesn't seem consistent.
It's very inconsistent. The paper suggests this might circle back to the training data. Maybe complex river crossing examples, high N, are just rarer online than complex Tower of Hanoi examples.
Meaning the model might have effectively memorized or learned the patterns for Hanoi better, but lacks the general ability to apply logical rules robustly to a structure it hasn't seen as often.
That's a strong possibility raised by the findings. It suggests the reasoning we're seeing might be less about true, abstract, generalizable logic, and more about sophisticated pattern matching that's brittle when faced with novel structures or scales beyond its training experience.
Okay, so let's try and synthesize all this. If you had to boil down the absolute key takeaways from this illusion of thinking paper, what are they?
Right, first, LRMs, the thinking models, do provide an edge over standard LLMs, but really only in that medium complexity zone.
But they hit a hard wall in high complexity, just like the standard models. Performance collapses.
Second, their behavior near that collapse point is weird. They actually reduce their thinking effort measured by tokens when the problems get hardest. Not what you'd expect.
Third, looking inside their thoughts reveals a messy process. Sometimes they find the answer early but keep going wrong, overthinking. Sometimes they search randomly and find it late. And at high complexity, they generate nothing useful. It's not clean logic.
And fourth, they show surprising struggles with just executing a given algorithm accurately for complex cases, and their ability to follow rules correctly is really inconsistent across different types of logical puzzles.
Which all points back to the paper's main question, right? Is this general reasoning, or is it incredibly advanced pattern matching that just breaks down under pressure?
Exactly. The evidence presented here strongly suggests limitations in generalizability, symbolic execution, and true robustness when problems deviate from familiar patterns or exceed certain complexity thresholds.
Wow. Okay, that definitely gives you a lot to chew on. So we've seen these thinking models, while impressive, aren't a magic bullet. They have advantages in a specific range, sure, but also clear limits tied to problem complexity.
And their internal processes and failure modes are, well, not always what you'd intuitively expect from something labeled reasoning.
The way they seem to reduce effort when challenged, the struggle with executing simple instructions when scaled up, the inconsistency, it really makes you question what that reasoning capability actually entails.
It's a valuable dose of reality about the current state of these powerful systems. Impressive, yes, but with nuances and limitations we need to understand.
Which leaves us, and you listening, with a final provocative thought to mull over. If giving one of these advanced AI models the exact recipe, the step-by-step algorithm to solve a complex version of a problem, doesn't really help it solve that problem. What does that tell us about how these systems understand or reason?
Is the real challenge for them less about finding the strategy and more about something much more fundamental, the ability to just reliably execute a sequence of logical steps, step after step after step, without getting lost, as things get truly complex?
Something to think about. That's all for this deep dive. Thanks for joining us.